Hi guys, it's Kate. We're going to talk a little bit about the function e to the kx in this video and why its derivative is k e to the kx. It's a fairly straightforward extension of what we worked on in class, and then you'll be asked to use this fact to compute several derivatives on your homework. But let's review what we discussed in class so far about exponential functions and their derivatives. The first thing that we discovered in class, first by looking at tables and then by confirming through a derivation, was that the derivative of an exponential function is a scalar multiple of the original function, meaning that it is the original function times some number. And this wasn't much of a surprise because when we attempted to draw a rough sketch of the derivative graph based on the original graph of the function, well, it looked a lot like the original function. This should come as no surprise once we do the derivation to find out, oh, the derivative of an exponential function is equal to some coefficient times the original function. Now, what is that coefficient? That coefficient, which we found through our derivation, and which we saw in the tables as well to sort of kick this all off, is the actual derivative's value at 0. Now, we looked at 3 explicit examples of b to the x. We looked at 2 to the x, we looked at 3 to the x, we looked at 10 to the x, and for each of those, they had a different value for the derivative at 0. For 2 to the x, it was about 0.69 and change. For 3 to the x, it was about 1.09 and change. And for 10 to the x, it was about 2.3. You can imagine as the base of the exponential function gets larger and larger, this value of the derivative at 0 is also going to increase. And one of the questions that came about in mathematics was noticing this fact. How cool! The derivative function for exponentials is proportionate to the original function. And that proportionality constant, or the thing that we're always multiplying by in order to get to the derivative function, is changing. Sometimes it's small, like when we're talking about 2 to the x, and sometimes it's a little bit larger when we're talking about 10 to the x. And a natural question that comes out of it is, what would the base need to be? What would b have to be? What are we raising to the xth power in order for that proportionality constant to just equal 1? So mathematicians began asking, for what value of b, meaning what value does the base of the exponential function need to take on? As in, we're looking at the functions b to the x. What does b need to equal in order for that derivative value at 0 to be equal to 1? And of course, if the derivative value at 0 is equal to 1, it would make this statement up here turn into this statement down here, which would be really interesting because that would mean that the derivative of the function was equal to the original function. And that number, which you can eyeball from our table, exists somewhere between 2 and 3. And you can continue getting more and more specific, experimenting and consulting tables to determine exactly where between 2 and 3 that seems to be occurring. But we gave it a special name. The name of that number is e. And so the following becomes true for the base e, that the derivative of that exponential function, when you raise this particular number to the xth power, the derivative of that function is equal to 1 times the original function, which is just the original function. So the derivative of e to the x is e to the x. So now we want to turn to what happens if instead of talking about the derivative for e to the x, we're looking at the derivative of e to the kx. Well, let's review for a second what happens when you transform a function by, instead of inputting x, where all of the inputs should go, instead you're inputting a multiple of x. Let's do an example like 3x. Early in their semester, we talked about what happened if you looked at a function f of x and then compared it to the same function but composed of 3x as its input instead of just x. And this corresponded to a horizontal compression. The y-intercepts would stay the same, but the function would be squished. The most straightforward example to look at is the simple function x and then 3x. What we notice is that the same change in function value, going from down here all the way up to here, happens in 1/3 of the interval when you look at it over f of 3x. So the function is still changing by the same amount, but it happens over a smaller interval in the domain as opposed to before. That's what the horizontal compression does. So the function is changing 3 times faster due to this horizontal compression. So when you're looking at something like kx, right, that means that it's going to be changing k times faster. The derivative at any individual point will be k times what it was before. Now thinking about the actual function e to the kx. Here's a comparison of the two functions e to the x and e to the 3x. We're going to use k equal to 3 as an example that we can work through. We notice that they share the same y-intercept, but there is this horizontal compression. And in fact, just like with the lines, there is an equivalent change in the function value over an interval that's a third the size with the blue function versus the red function. Let's take a look at what's happening at the value of the derivative at two different places. Once at x equals 0, and then let's take a look at maybe x equals 1/3 on the blue function. At x equals 0, both of these functions have the same function value, right? You plug in 0 for x, and whether you're looking at e to the 3x or e to the x, you're looking at the same point that it goes through on the graph, right about here. But then, when you look at the slope of the tangent line to each of those individual functions, suddenly you start to see the effect of what happens with this horizontal compression. The slope of the tangent line to the red function is much more relaxed. It would look something like this. The slope for the tangent line to the blue function, e to the 3x, is way, way steeper. It's like this. And so it's that fact that the function is changing 3 times as quickly in order to cover the same quote-unquote ground over a smaller interval that is affecting the derivative. The derivative itself at an individual point is 3 times what it would usually be. Let's think about what's happening at the point 1/3 on the blue function. Now, what's the corresponding point on the red function e to the x? I mean, this point here, the green point, it came from somewhere. If we're talking about this as a horizontal compression, which point was it compressed from? It was actually compressed from way out here, right? When you plug in 1/3 into e to the 3x, you end up with e to the 1, which is the input over here at 1. So you can imagine that this is the point on the function before the horizontal compression. This is the point after, once you've squished it in. Now I've tried to draw in both the points as well as label their inputs that correspond to those points and draw in a little piece of a tangent line to the curve at these various points. And what we start to notice is, well, one is much, much steeper than the other. Now on the red function, e to the x, we know that the derivative of e to the x is e to the x. So if we're at 1, the derivative at 1 is going to be e, right? The function value is e there, and we're told that the function value is equal to the slope of the tangent line at that point by saying the derivative of e to the x is e to the x. So I've labeled it. Now what's happening over here? Well, it's much steeper. If it was before the horizontal compression, that point would have a tangent line with slope e. But after the horizontal compression, it has an even steeper slope. And that's because the function itself is changing at 3 times as fast a rate. Because of what we discussed before, right? When you do a horizontal compression, the same amount of change in the function value happens over a shorter interval of the inputs. So what's interesting here, what we found is it's not just that the derivative for an exponential function, e to the kx, is equal to itself. It's equal to k e to the kx. Whatever that multiplier is up there is causing a horizontal compression, which means that the function is changing k times faster than it usually would be. So it's no longer sufficient just to say, oh, the derivative of the exponential function e to the x is equal to e to the x, and that's going to be true for e to the kx, that the derivative of that is equal to e to the kx? No. That multiplier means that the slope of the tangent line is also getting multiplied. So that is how we arrive at the fact that the derivative of an exponential function that has a multiple of x up in the exponent up here, where k is any constant, e to the kx, it means that the derivative is equal to k times the function value. I hope this helps. There are solutions to the worksheet that go through talking a little bit about secant lines, but feel free to fast forward, rewind, or even email if you're still unclear about why this fact is true.